My name's Danielle Liut.
My name's Abby Buller.
And my name is Nick Vrzovski, and our capstone is called Sunflower. This project was made in partnership with Lux Aerobot.
Lux was the first Canadian company to successfully launch a stratospheric platform to accomplish Earth observation. That first launch was in 2022 and lasted 3 hours. In order to launch successful platforms with flight durations of days and weeks instead of hours, and to incorporate more sophisticated payloads with higher power consumption, the problem of onboard power generation must be dealt with.
The goal of this project was to design a custom-built solar generation solution for Lux's high-altitude platforms to maximize output power and flight duration while keeping cost and weight to a minimum.
Up to a certain point, the more incident light, that is, the light that strikes the surface of a solar panel, you have on a solar panel, the larger the power output you will receive. Our solution incorporates two principles in order to maximize the amount of incident light on the solar panels.
It is known that incident sun rays that are perpendicular to the panel generate more power than rays that strike the surface at other angles. We have designed a solar tracking system that works to ensure that our panels remain perpendicular to the sun's rays as the sun moves across the sky during a typical day. We do this in two ways. The first makes use of a solar position algorithm, which uses geographical coordinates to calculate the current position of the sun relative to the platform, and then moves the panel so that the surface is perpendicular to any incident sun rays.
The second method also works to ensure the panel remains perpendicular to the sun's rays, but does so by intaking and comparing resistance readings from two photoresistors on the surface of the solar panel. When photoresistors are exposed to light, their resistance values decrease. With our setup, both resistors will only receive equal amounts of light when the sun's rays are directly perpendicular to the surface of the panel. If the panel is tilted in a suboptimal manner, one resistor will be shaded from the sun by our little divider. The resistance values of the two photoresistors will not be the same, and the system will take that as a sign to adjust the tilt angle of the panel.
The tilting is accomplished using a pull-pull system. Two ropes are attached to the top and bottom of the panel respectively. A motor rotates a spool which tightens one rope while simultaneously loosening the other rope to allow for tilting to occur. With a gear in place between two spools, one motor is able to control the tilting of two panels simultaneously. This system uses less power than having to use twice the amount of motors and is substantially less expensive and power-consuming than using linear actuators to move the panels.
The other method we have implemented to increase the amount of incident sunlight on our panels is through the use of reflectors. This method works to direct more light onto the surface of our panel. The dimensions of the reflectors and angle at which they sit in relation to the surface of the panel were determined through modeling and simulations. Our modeling was done in Zemax. Our panel was modeled as a detector rectangle. We chose reflective surfaces out of which to build our simulated reflectors. An array of reflectors of different sizes and tilt angles were simulated, and the amount of surface irradiance was recorded and compared between trials. It was clear from the simulations that some angles and dimensions were better than others. We then took the best performing setups and compared their power generation to their weight and cost. We ended up selecting reflectors with a length of 20 centimeters and a tilt angle of 118 degrees from the surface of the panel.
In order to determine the most optimal power generation setup, we created 4 different setups on the 4 sides of our gondola. One side has a vertically stationary panel, one has a vertically stationary panel with reflectors, another has a panel that tilts to always face the sun with no reflectors, and the final side has a panel that tilts to face the sun with reflectors.
After testing the power output from all 4 solar panel setups, the tilting panel with reflectors showed the highest output power, while the stationary panel without reflectors outputted the lowest power. These results agree with our simulation data. We are looking forward to working with Lux to integrate features of our design in their platform.